What's going on, folks? Today we're going to learn about exponential functions, okay? This stuff right here. Now, typically with the functions that we've been dealing with, you're used to seeing something along the lines of like y is equal to x squared or y is equal to x cubed, okay? Something to where you have an x value and it's being raised to some exponent, okay? We know how to deal with this because you just take whatever x is and in one case you square it. And in another case, you cube it, but you will do the same thing each time to just whatever the different x value is. Now, the difference today is what happens when you flip these things. What if, instead of having the x as the something being raised to a power, what if you had something being raised to the x power? So, for instance, instead of y is equal to x squared, what about y is equal to 2 to the x? Or instead of y is equal to x cubed, actually having y is equal to 3 to the x, where that x is now the exponent. That's an exponential function. Now, I'm going to break it down a little bit and talk about transformations and the different parts, but this is essentially all it is.
I'm wrong. Should have done better than this.
All right, now all of these functions have some kind of a vertex form that we can use as far as figuring out the parts and the location of this graph. Now, these exponential functions are going to have the exact same type of stuff, but I'm going to include one letter. Now, the actual form for an exponential function is going to be y is equal to a times b raised to the x minus h power plus k. Now, I know that's a mouthful, so I want you to take a real special look, okay? We're used to seeing the A, we're used to seeing the H, and we're also used to seeing the K. And almost all of them are in the exact same positions. A is the number out front, H is the number that's paired with the X, and K is the caboose of the train. K is that number that's at the very back. The only thing that is different in this case is that B for the base. And that's whatever number is actually being raised to the exponent of x minus or plus whatever number happens to be there. So B stands for the base.
Show me what I'm looking for.
Now we're actually going to get down to what really makes an exponential function, but there's going to be two parts that you have to use in order to be able to make it. Now, the first of which that we're used to normally seeing, I'm going to start with the vocab you're used to, and then we'll branch out. The first two things you normally see are some kind of a vertex or a starting point that can be found using the two values h and k, where h is going to give you the x value and k is going to give you the y value, so you can find a point and then move on from there. Now, the other thing that you're going to have is going to be some kind of an axis, be it either an axis of symmetry or a slope or something that kind of lets you know how to line things up on this graph. We got a similar one, but it's a little different. Now, let's start with the vertex. As opposed to using vertex, we're now going to use the term the initial point, where initial stands for the first. Now, I'm going to use the expression IP, but when you see that, know that I mean the initial point. Here's how it changes. The h stays exactly the same, so we got the same x value. But for the y, as opposed to having a k, the k is still going to be there, but we're going to add in something. And we're going to add in a. Okay, to where your x value for this point is h, and the y value is the sum of the two terms, k plus a. As soon as you can plot that point, you'll be good to go. All right, now instead of this axis that we were talking about a second ago, we got another term that you're going to need to know. Now, we've seen it once before, but just in case you don't remember, what this is called is an asymptote. Okay, this one right here, an asymptote. And what that means is to have a boundary line that the graph never quite actually touches. This will make a whole lot more sense when I actually start to graph these things, and you'll be able to see this stuff up close and personal. But just know that we have an asymptote that's going to be a reference line. Now, the equation for that reference line is going to be when y is equal to k. Okay, we'll look back up at our original function in order to figure out what k actually is. Remember, that's the caboose of the train, whatever number's actually at the back end of the whole problem. and whatever that number is, you can think of a horizontal line, y is equal to that k number, and that will give you your asymptote, a dotted horizontal line that serves as a reference boundary for the rest of the graph.
Please, I'll be strong. I'm finding it hard to resist.
Okay, so here's an example of one of these exponential functions. We've got in this y is equal to negative 2 raised to the x plus 2 power minus 3. So before I can even worry about graphing, I need to identify what I have. So let's go ahead and take a look. The easiest thing to start with is going to be b for the base. So what I'm looking for is whatever number is actually being raised to the exponent. Now the important thing here, and the number one mistake in this problem, is that most people will think, oh, negative 2 is the base, but not really. If I break negative 2 down into two numbers, I'll really get negative 1 times 2. Now if that's the case, looking back up at my original problem, and here let me erase this so that way that it makes sense. I've now got a negative 1 times 2 raised to the x plus 2 power minus 3. So a is whatever number is out front, in this case negative 1. B is whatever number is being raised to the exponent, in this case a 2. H is whatever number is coupled with that exponent, so in this case it's an x plus 2. But because it's minus h, I have to take the opposite of what I see. So it was positive 2, the opposite is a negative 2. And then lastly, k is the caboose of the number at the end, so now I have a negative 3. So now that I have these things, let's go ahead and actually put them on our graph. Okay, now the two parts that we needed to graph this were our initial point and the asymptote, and these were the ways that we found them. So all we really have to do is plug in the numbers we find. So I need h, k plus a. Well, h is a negative 2, so I just plug that in and I've got my x value. The y value is k plus a. So negative 1 plus negative 3 gives me a negative 4, so I can plot that point. Now I look over here at the asymptote, it's y is equal to k. And if y is equal to negative 3, then I'm going to plot a horizontal line along y is equal to negative 3. Now I need to figure out what happens to this graph as I move to the left and what happens when I move to the right. So I'm going to use an x and a y table. And if it was at negative 2, negative 4, I'm going to figure out what happens to the left at negative 3 and what happens to the right at negative 1. When I plug these into my equation, okay, negative 1 plus 2 is a positive 1, 2 to the first is 2, times negative 1 is negative 2, minus 3 is a negative 5. When I plug in negative 3, I get 2 to the negative first, which flips to 1/2. Negative 1/2 minus 3 is going to give me negative 7/2. And then I can plot both of these points. And that's basically it. That little almost 90-degree curve around the corner is my graph. That's it.